Hey guys, in this video we are going to discuss briefly about the history of radios and then we will move on to the FM radio receiver circuit. Radio was one of the greatest inventions of the 20th century. It created immense impact in the faster transmission of informations across the globe. In 1873, James Maxwell showed mathematically that EM waves could travel through air. Heinrich Hertz in 1888 demonstrated Maxwell's theory that electromagnetic radiations could be produced and detected. In 1892, Nikola Tesla demonstrated the sending and receiving of radio frequency energy. However, the credit for the first wireless transmitter goes to G. Marconi. His device could send signals up to 1.5 miles. One of the first widely produced and widely used radio sets were the crystal radio sets. By 1920, these sets had become quite popular in the American household. All the radio sets up to this time used AM waves. The problem with these amplitude waves was that they were short-ranged. In the year 1933, Edwin Armstrong invented FM waves. These frequency modulated waves used in the FM radio were long-ranged. With the invention of FM, radio only needed one more evolution to become what we know today. That last advancement was the transistor radio.
Now we will show you the working of a FM radio receiver.
Here is the block diagram of a radio receiver circuit. Now I am going to explain the flow of information in the circuit. The input signals available to the circuit are electromagnetic waves, but the circuit works on electrical signal and the antenna serves the purpose of converting the EM waves to the electrical signal. The electrical signal from the antenna contains all possible frequencies. The preselector filter filters out the frequencies of the radio band. The output signal of the filter is very weak, so an amplifier is used to amplify the signal. Now Wasih will explain us why a mixer is needed.
As explained by Ataul, the input signal contains variable frequencies. Therefore, it is difficult to process this signal and it may give poor performance. This problem is solved by mixing the input frequency with a desirable generated frequency, and thus it produces a fixed frequency called the intermediate frequency or IF, and it improves the performance.
In order to ensure that only the created intermediate frequency passes through, an IF filter is used. Now, the demodulator decodes the electrical signal into the required sound signal. Finally, the output sound signal is amplified and transmitted by the loudspeaker. Now I am going to discuss the working of the above circuit in detail. In the first stage of the circuit, that is at the preselector filter, we basically allow the frequency band of the radio waves to pass through. For this purpose, a series RLC band pass filter is used. It can be shown that the allowed bandwidth is given by delta WP is equal to Ri upon Li, and hence Ri and Li can be adjusted to allow the radio band of around 88 MHz to 106 MHz. The amplifier uses an op-amp to amplify the input signal. It can be shown that the gain for the op-amp is Vout upon Vin is equal to 1 plus Rf upon Rin. Next, we feed the input of the amplifier and the local oscillator into the mixer. Local oscillator generates AC frequency by the parallel connection of Li and Ci. The induced voltage in L2 allows the feedback circuit to send amplified responses to parallel L1 and C1. Hence, these are fed into the mixer. In the mixer, the diodes used ensure that either the sum of the two input signals or the difference of the two input signals are generated. IF filter is just another RLC band pass filter. Next, the input is passed into the demodulator where the diodes D3 and D4 produce a steady voltage across R6 and R7, and hence the capacitor C9 charges up. The transformer enables the circuit to detect the changes in frequency of the incoming signal.
Now I have a question for you. Suppose that a user wants to select 93.5 FM radio frequency. Which component of the radio receiver will help him select the station? Also explain the working of the circuit in making the selection.
Let's say original frequency station was F1 and oscillator frequency obtained from LO was F2. Then the intermediate frequency IF is equal to F1 plus F2 or F1 minus F2. It is generally low, so it will be F1 minus F2. Now, if the station is changed to a new frequency F1 dash, then oscillator frequency must also change to F2 dash to maintain the same IF. Hence, we may change the oscillator frequency F2 to F2 dash and hear the station at frequency F1 dash. F2 dash will be equal to F1 minus F2 minus F1 dash. F2 is given by 1 upon 2 pi into 1 upon under root L1 C1. Hence, if we change capacitance C1 of the oscillator circuit, we can go to the desired station.